Hello everyone. Today's lecture is the measurable function. In this lecture, I want to say the concept definition of the measurable function, in particularly the Lebesgue measure space. In prior to starting our lecture, let's recall our long travel in the measure theory clip. Firstly, I'll introduce the definition of the Riemann integral. Riemann integral is very familiar integral right now. However, this is a big problem. Let's see the Lebesgue theorem. Lebesgue theorem is here. Bounded real interval Riemann integral if and only if the set discontinuous of f has measure 0. So even though the discontinuous point has discontinuous point is countable on the domain, this is no problem to evaluate the integral. However, let's see in this case. This is clearly not Riemann integrable because we can see the reason why. We can understand why these guys not a Riemann integrable. The first reason is namely the definition of the Riemann integral, the upper sum and the lower sum. These guys, lower sum is 0. However, upper sum is 1. So because of this is not integrable. And we can see because discontinuous, we can when you consider the Lebesgue theorem, because this is if and only if relation, discontinuous point discontinuous point is not measure 0. Okay, because discontinuous point occurs in the irrational number, but this is clearly non-zero. So by the Lebesgue theorem, this function, bounded interval function, this is clearly bounded real interval on closed interval. This is not Riemann integrable. However, intuitively, I think that many people think that the value would be clearly, when considering the floating image, this integral would be 1 is better. However, because of the Riemann definition of the Riemann integrable, or because of the Lebesgue theorem, this integral from 0 to 1 is clearly not integrable in the Riemann sense. So in order to solve this problem, to become such function change into integrable, many mathematicians consider new idea. So to understand, to do this, we absolutely have some knowledge about the measure space. So lecture 14 to 18, I explained some numerous concepts of the measure space: Sigma-algebra, Bohr-Essay, auto-measure, pre-measure, Hancara theory, extension, and so on. So Lebesgue measure is the general, when you consider, we can, in this lecture, we construct the generalization of the measure space, and Lebesgue measure is an example of general measurable space. Okay. This ingredient is useful and essential rather than essential. Next, our aim to Lebesgue integral. Lebesgue integral is new tool in order to overcome the limit or trouble of the Lebesgue integral. Riemann integral. So in this lecture, lecture 19, after 19, I will explain Lebesgue integral, the little different sense of the Riemann integral. However, because we apply Lebesgue integral, we can integrate such function. This is clearly not Riemann integrable. We can evaluate the value in the Lebesgue integral sense. Go ahead. First, in this lecture, I will the fundamental concept of the Lebesgue integral. Next lecture 20, we will see the form of the integral, how to integral and the property and so on. Next lecture, after lecture 20. Okay. Anyway, let's see the definition first. Let's read the definition of the measurable function. Of course, this is the general case. This is always this is because it's general case. We can say the Lebesgue measurable function. Later we refer this here is just an example of the measurable function. This is general case, and Lebesgue is an example of the general type. Okay. Anyway, let's read the measurable function. Let x a y b. Sorry, this is a grammatic or typo. Let x a and y b be a measurable space. A function f x to y is measurable if its inverse. For any inverse element, b is the sigma-algebra in y. These guys in also measurable in x. So this is, we can always distinct. A is the sigma-algebra in x, and B is the sigma-algebra in y. So for every, we can pick in y. Just drawing the picture. Let's choose function. Choose y. B. Okay, so B is clearly sigma-algebra. Because this is a general case, this is so abstract to understand this. Anyway, let's try to understand this statement. This guy's F inverse B. So whenever we choose in sigma-algebra element in y, such inverse is sigma-algebra in x, then we can say the function f is measurable function. In this case, object is measurable, is function. Okay, the object is function. The function is measurable, such condition satisfied. Then let's see the useful proposition in this lecture. Suppose these guys are measurable spaces, and B is the Borel sigma-algebra. Is this here? Notation, remember the notation? The smallest sigma-algebra. Smallest sigma-algebra containing, which contains G, fancy G, calligraphic G in Py. Then F is measurable if and only if we can check the Borel set. If we studied in topology, for example, F is continuous. The original definition exists, but we can check just, it is no problem just to check the base for y. In inverse of the base is still base for x. So we just check this here, restrict the range, our range, the Borel sigma set. This is no problem. The function is measurable. So let's prove this theorem. Because this is if and only if condition, we can check the direction is here, and the other side we can check all side or all direction of the arrow. Then let's prove this theorem. proposition. This direction, our assumption is F is a measurable set, and our claim is every inverse image is in the sigma algebra in A. So for convenience, I set the definition R is the collection of F inverse G in G in fancy G. Our claim, this guys is measurable set. Or not measurable, sigma algebra condition. Okay, the collection of the inverse image, this here is sigma algebra. Note that when you consider the definition of the Borel set, G is always contained sigma G, because this guy's original definition is contains the smallest sigma algebra contain G. So in fact we can say G is also element in Borel set. We can check this here. So we can say G in sigma algebra G is really satisfy the sigma algebra condition. To check this, our assumption is R, the collection of R is the sigma algebra. So our claim is that when considering the definition of the sigma algebra, we check three properties: empty set and whole set, absolutely element in R, and complement condition and countable unity condition. So let's check this. First, this element really contained element empty set or whole set. This is okay because this here, because G is an element in the Borel set. Anyway, this is also the sigma algebra, but the smallest sigma algebra containing element G. So empty set and whole set is clearly the essential condition for the sigma algebra. Because this is RI sigma algebra, this element should be contained. Okay. Then instead, in this case, because this domain G is in Y, we can say empty and Y in this here. Then F inverse empty is empty, and F inverse Y, when we consider the definition of the function, this is Y X. So empty set and X in contained R. We can take the first condition. A second is complement condition. Suppose G, because G is, I already said, sigma algebra, but smallest sigma algebra containing G. Anyway, sigma algebra satisfies the complement in this here. Then, when you consider the R is the element this set, so we can check this is really contained in R. Then we can say first F, this does, because of the set theorism, we can say G, F inverse G, it complement in C. And note that by assumption, F is the measurable. What is the definition measurable? For every element B in B, in this case, okay, B, F inverse B is R. This is our assumption, and this here, this is B in this case here, B. So by assumption, this is in R. Okay. Then, anyway, this is sigma algebra in A. Then, because this is sigma algebra, its complement is also sigma algebra. So this is also A. The second property is satisfied. And the last condition is unionized condition. In this case, we can consider also, because this is sigma algebra, a union of Gi, where is Gi is in the sigma algebra element Borel set, okay, Borel set in G, for each I, this is also in Borel set. B. Then we consider the inverse image, F inverse Gi. Because the set theory, we can say this is there. But note that because Gi is the B element in B, this is also, when considering our assumption, this F inverse IGI is in R. However, so because it's sigma algebra, the union of the sigma algebra is also in R. So, because these three properties is satisfied, the collection of the inverse image is sigma algebra in X. So, first we can check the first properties are satisfied. This direction is satisfied. And then let's prove the other side of the in this proposition. This here. Let's see this proposition again. Our assumption is here. This, and I want to show this F is measurable. What is the measurable? Definition of the measurable? This means our claim is for every B in B is F inverse B in the sigma algebra R. And in this case, remarkable point, B is the Borel set, the smallest sigma algebra it contains in the set G. For the proof, I define the set M, fancy M. This guys, the subset of Y, which consists of F inverse B in the sigma algebra in R. I claim that this M is sigma algebra. This is easier to check the three properties of the sigma algebra. And okay, this is here. And note that the G is subset of M. Why these rules are satisfied? Because this is our assumption. Because G is the power set of Y, fancy G subset of Y, and this here, G is element in G. So first check that when you're considering the definition, G is subset of Y, and this, because every element in G and fancy G satisfies this here, we can check these rules also satisfy. So G is clearly subset of M. And this G is also sigma algebra. Then our assumption is every sigma algebra Borel set in here, every inverse image, pre-image in sigma algebra in R. So clearly, however, we consider two cases of this here. The first case, element B contains in G, fancy G, otherwise B is clearly not in element in G. Why? When considering the Borel set, how to construct the Borel set? Borel set is the smallest sigma algebra containing some element. For example, x1 to 3, B1, B3 is one of the sigma algebra, and intersection is the smallest sigma algebra containing 3. But in this case, clearly 1 and 2, these guys does not element in G. Okay? So we can consider B in case in element in fancy G, and otherwise this case. The first case easy because if we contain this case, B is G, and G, because G is element in G, is subset of M, so this is here. Okay? Because B is subset of M, this means, what is the B is element in M? What this means? F inverse B is element in R. So in this case, whatever we choose G, element in G, F inverse B in element in R. However, in second case, it is little tricky. I think that, in my opinion, little complex to check this. I'll explain why in this case satisfies this relation, our claim. So in order to do this, I introduce some definition. Originally, it is right introduce the measure theory, measure space. However, because I do not refer the concept, in this lecture I'll explain concisely. So, the definition of the monotone class, the class M is the monotone class if AI in M, and this rules AI and AI plus 1 for all I, then, and so if this here and this rules are satisfied, then union of AI is in M, we can say a class M is monotone class. And you can directly check that every sigma algebra is the monotone class. Another thing, the concept we should understand is the semi-ring. In the previous lecture 17, why we need the semi-ring? Semi-ring needs to extend if we extend the set into the measure space, so construct these guys, the minimal condition, the set the arbitrary subset can construct the measure space. So by using the set as is given to it, we can extend sigma s, the smallest sigma algebra. So we extend the s to the measure space M, but the minimal condition to construct the measure space S requires the semi-ring condition. Because S can be a semi-ring, we can construct the sigma algebra. So, in this case, if we consider G, and we consider sigma G, because this is clearly sigma algebra, then the minimal condition G is at least semi-ring. Okay? The minimal condition. So G should be the semi-ring. And another fact I did not refer in this lecture, any element in A in the sigma algebra is generated by union of the semi-ring. What this mean? I will say G is given, and we can construct sigma G sigma G, fancy G is clearly bad, we can say this is sigma algebra. Okay, so if element A is in this element, by our respect, this here, A is absolutely unionized of the GI, where GI is the semi-ring element in G. Let's go back to our second case and let's check this here. In this means, more precisely, B is the element in the Borel set. Okay, but B is not an element in G. Because this is clear, every element in this element, okay, and the definition of the sigma algebra, the smallest sigma algebra containing G. So the case B in G, our claim in this case and in this case, two cases. First case, this here, this is true, and second case, this here. So we can check this case. Whenever we choose element, this here, okay, this here, our final claim is B is also in M. This is our R. Okay, then our proof is finished. Will be finished. Let's go back to our proof. Let's check this case. More precisely, we can say this is B is element in the Borel set in G, but B is not in G. Because this is clear, G is a set, and Borel sigma algebra is the smallest sigma algebra containing G. We can check any element in this case in inverse image in A, and the first case, this here, this is element in G. This is clearly its inverse image in the sigma algebra in X, and we should check this here. Okay, so this is sigma algebra Borel set. B is in Borel set, but this is not in G. We can check in this case. Okay, then let's prove this here. Only concentrated on the second case. At first, note that B is Borel set in G. G is just a set. This is the sigma algebra Borel set, more precisely Borel set, the smallest sigma algebra containing G, so G should be a semi-ring. Okay? By our pact, I remarked in this here, every element in sigma algebra is generated by union of the semi-ring. So, because of this, because G is clearly semi-ring, and B is the sigma algebra generated by G, so this expressed union of V I rather than Gi. What is Gi? Gi, every element index I, Gi in G, for our index I, G is absolutely semi-ring. And remember that the previous note, every G in G element is subset of M. So, because of this note, every Gi is also subset of M. Okay? Then another remark is that every sigma algebra is monotone class. Then because M is the sigma algebra, okay? So because it's sigma algebra, this can be the monotone class. So this means if we construct G1, G2, blah blah blah, every union of Gi is subset of M. Okay? We can construct this process because this guy is a sigma algebra, and this G1, each index Gi is clearly in subset of Y. So this this way defined on the set M. So union of Gi is in fact B, and because fancy M is monotone class, this guy is contained in M. So whenever we choose B, which not is an element in G, we can construct these guys also in M. So because these rules are satisfied, we can check the first case, this here, and second case is here also satisfied, and we can check that our this claim is satisfied. This means f is measurable. And let's see the measurable function on the Lebesgue measure space. In the previous slide, I introduced the general measure space. In this case, Lebesgue measure space. So, when comparing to the general case, if just change r real number instead of y, and this function is called measurable if its preimage, whenever we choose in Borel set, B, its inverse image is sigma algebra in A. Of course, the definition of the Borel set is the smallest sigma algebra containing open interval I, and every interval can be the Borel set. So we can understand whenever we choose the interval because interval is the Borel set. Whenever we choose any interval in R, its inverse image is also if its inverse image is a sigma algebra, then we can say this is measurable function. And in the real, if domain is changed the real number instead of x, and the range is also real number, this guy is called the Lebesgue measurable when we choose the Lebesgue measurable subset of whenever we choose every Borel set B in R, its preimage is also Lebesgue measurable. Then we can say the function f is the Lebesgue measurable set. Lebesgue measurable function. Okay, it is so boring to just read the definition. So okay, let's see an example of the Lebesgue measurable function. The composition of the Lebesgue measurable function is Lebesgue measurable. What this means? Let's consider x r and y b and g che. Okay, this is fancy alphabet b che, and let's see some function f. It is a Lebesgue measurable function, and g is also Lebesgue measurable function. Our claim is the composition of the, if fg is the Lebesgue measurable function, the composition of g dot f is also measurable function. It is just to check the definition of the Lebesgue measurable. Whenever we choose element c in Che, because g is measurable, g its inverse image C is contained. This is a step. Okay, this is a large capital. C is contained in B. And because again F is also measurable, and measurable whenever we choose element in B, because this is also no problem, its inverse image F inverse G C is element in R. This means G dot F inverse is here. Our claim is clearly true. Whenever we choose C, the sigma algebra in G, its inverse image is also sigma algebra in A, so the composition of the measurable function is also measurable if two functions are measurable.
Following proposition, f is x to r. This is function, then taking following are equivalent relation. First, f is a measurable, and this is equivalent to for any collection of x, fx smaller than b is sigma algebra in x whenever we choose arbitrary element in b. And next is analogous, looks like similar to statement b, but in this case contain inequality. So f b will be in R. And D, in this case, the inequality is changed for arbitrary element in A. And lastly, containing equation. This is the following condition of the measurable function. If x, domain x in the range in the real number. Okay, then let's prove the statement. Because this is the equivalent relation, we can prove A to B, B to C, C to D, D to E, and lastly E to A. So let's go start. From A to B, because this function is measurable, what this means? Our assumption is every Borel set is given, its inverse image is sigma algebra in A. And remark that this collection of the set means fx smaller than b. We can write this fx is this open interval. Okay? And then by definition of its inverse image, x is image of f inverse minus infinite to b. This is the same set as collection of x such that fx is smaller than b. But note that this form is the open interval. So this is the Borel set. Element in the Borel set BR. By assumption, because this is the measurable, its pre-image is by assumption in the sigma algebra in A R. So we can deduce from A to B. And in case of B to C, our assumption is here, and we can obtain the result C. This means finally we will get f inverse minus m infinity to b. When we consider the definition, this here is element in R. This is our final result. Okay. We in order to obtain this, I'll define minus. I consider the set this here and unionize. This value is clearly minus infinity to b, but the type of the such set is the open interval. If take inverse this set, then this result clearly f inverse minus infinity to b. And we can, by the set theory relation, we can write this is here. And by assumption A, the type of this is clearly in sigma algebra in X. Because this is sigma algebra, arbitrary union of the sigma algebra is also in A. This is same as this here, so we can deduce from D to C. Also, we finally B to C, we can obtain B to C, and let's go ahead. In this case, I want to prove B to C, C to D. We know the following type of form is clearly sigma algebra in X. So this means f inverse minus infinity to b, but in order to prove in obtain to d, I'll use the notation a instead of b. This is no problem. This guys is in R by the assumption of the C. Because this is sigma algebra, its complement, this here, is also in sigma algebra. But by the set theory, we can write this is minus infinity to a, its complement, and this is same as a infinite. This is clearly, again, correction of x, fx is greater than a. This is in R. We can deduce C to D, and similar, something like B to C, we can deduce D to E. What is this? We can express A clopen, A infinite is by expressing A minus 1 over n to infinite. So we can deduct, by doing this, we can deduce D to E, statement D to E, and we can similarly C to D, this is the way C to D, we can deduce C to B, E to B. So we can prove A, B, C, D, E is given. We can check A to B, B to C, C to D, and D to E, and I want to get D to E to A, but I will get I obtain E to B. So BCDE is equivalent relation. However, this is because this pole statement is equivalent relation. By using this is true. By using this condition, we can easily deduce the statement A. So all type of the Borel set, because all type of the Borel set is expressed by the type of B, C, B or C or D or E. For example, when we consider AB, we can express AB is minus infinity to B union of A to infinity. So this type is the A, B, and this is D, statement D. So we may take its inverse image. Clearly this is the Borel set. This is here, this here. So this is measurable in X. This is also measurable in X. And the union of measurable set is also measurable. So this is sigma-algebra. So because all type of the Borel set is expressed by type of B, C, D, E, we can deduce this arrow. So all of the statements is equivalent relation. And let's see the following proposition. If fg is a measurable function, then and k is in real number, then times of k in f plus g, f times of g, f quotient of g is type of our measurable functions. To prove this, we use the equivalent relation I introduced. So, but however, one of them, in case of kf, is so easy to prove. This is your exercise. I want to prove another case, f plus g, fg in f quotient of g. So in order to prove f plus g is measurable, I think the equivalence relation is here, and I use this condition. Remember this condition. So I want to consider the collection of the x such that f plus g in x is smaller than, in this case I define alpha. I want to claim this is the set of collection of the set. This is not logical. This is logical. Just collect the set. I'll claim this guy is an element in the sigma algebra in X. Because clearly the set X is collection of following condition: fx plus gx is smaller than alpha. Again, this means fx alpha minus gx. Then in this inequality, I apply the Archimedes principle. What is the Archimedes principle? This is not equivalent relation. There exists rational number such that between fx and alpha minus gx. This is the Archimedes principle. The point is that this is rational number. Okay, this is when you can say this is fx, this equation means fx is smaller than r, and in the sense of the gx is this goes here, gx goes to here. Okay, alpha minus r. Okay, alpha minus r. Then we can express these guys is unionized in the rational number, such that in case of the fx smaller than r, and this case, this point, this is because this relation is and this here. X is smaller than alpha minus r, quotient of x. Okay. Then check that the intersection. Okay, first check, because f is measurable. Our assumption f and g is measurable. So this is equivalent relation of the measurable condition by statement B. This is condition of measurable. And this is also because G is a measurable set. This means this is a measurable set. The intersection of the measurable set is also measurable. Always remember that, although the condition does not contain the definition of the measurable set, but we can express intersection of B something like this. So the union of the measurable set is also measurable, and its complement is also measurable. So the parentness, this guys, is a measurable set. And the union of countable union of measurable set is also measurable. Remember that because this is usefulness is the when you consider the definition of the measurable function, countable union of measurable function is also measurable. During the lecture, I'm sorry for arbitrary union. I refer that arbitrary union of the measurable set is measurable. This is wrong. Instead, countable union of measurable set is measurable. Anyway, this guys is in the measurable, in particular sigma algebra in A. So this correction of this is sigma algebra in X. This f plus g is a measurable function. Okay, good. And check the condition. This here, f product of the function. Most interesting point, we can express f product g is written as help f plus g square and f square minus g square. Then, okay, then our claim in this situation, I want to claim that f square is measurable. if this statement, its claim is really true, then this guy is measurable, and because the addition of the function is measurable, this guy is measurable, and because of this 1/2, this parenthesis is also measurable, so the product of a measurable function is measurable. To check this, I also use the equivalent relation of this proposition. And our assumption is already f is a measurable function. So I consider the collection of f square x is greater than alpha. This means when we solve the equation, this guys, f square x minus alpha is greater than 0. This means fx is greater than alpha, root square alpha minus alpha, or greater than okay, direct factorization. So this means fx minus alpha fx plus root square alpha is bigger than 0. This means fx this alpha, this is fx smaller than alpha, or fx is greater than alpha. So we can, using this, we can express x fx smaller than alpha, because this is, or I express union x is greater than square alpha. But because f is measurable, for arbitrary real numbers comes, this here, these guys are measurable. And union of the measurable function is measurable. So because of this, f square is clearly measurable. So our proof is okay. Okay, finally check this f quotient of g is measurable. Okay, our claim is, however, our claim is just to check that g1 of g is a measurable function, because we can express f quotient of g is f product of 1 of g. Okay, so if it is true, then because the product of the measurable function is measurable, then the quotient of the function is also measurable. And to check this is equivalent relation. The collection 1 of g is alpha for arbitrary in real number. Then let's consider this collection, and I want to express the function is in terms of g, because by the assumption g is the measurable function. However, we consider the sign of the alpha. The easier example is alpha is the positive. In this case, when consider alpha is the negative, absolutely g is a negative. Okay? So when this in this inequality that we can express, because G is the negative, this here, alpha G, and if in terms of G, to express in terms of G divided alpha, but alpha is negative, 1 over alpha is smaller than G. And by the condition, G is smaller than 0. So if alpha is positive, we can express G is greater than 1 over alpha, and intersection, because this is G is smaller than positive. And note that because G is measurable, this forms is also measurable. This is also measurable. This is in R. When you consider this is R, then this is also R. So because this is a sigma algebra, and its intersection of the union is also sigma algebra. So in this case, alpha is the negative. This guy is measurable. Similarly, we can check in case of the alpha is 0, alpha is positive. When alpha is 0, then the range of the G is here. So in this case, this is also measurable function in X. So this guy is also measurable. And this is a little complicated because even though alpha is the positive, we consider the case, even though alpha is positive, G can be the positive, because this is, for example, okay, alpha, for example, putting just 3, so 1 over G is 3, smaller than 3, then G is also positive, or G is negative. And of course, G, however, in this case, G cannot be 0. Okay, this is no. So we can consider two cases of the G. By consider two cases and express G in terms of G, the result is here, and the union of, because two case is or, this is expressed union 1 over alpha, G is, in this case, so this is infinite. Okay, so in this case, G is the negative case, and this case, G is a positive case. Anyway, this is also measurable set. So because this all, when you consider all of the case, G following G is a measurable, so this is also measurable. And let's record the definition of the almost everywhere. This condition is very frequently frequently show this concept after next lecture. A property P is set to P almost everywhere in X. The property satisfied except from major zero set. Okay, so our proposition is, if F is a measurable function and Fg, okay, this notation is important, A comma E, this is the short for almost everywhere. Okay, this A, E. So this means f is equal to g, but only in this case except for measure 0 for all x in x but set minus n where mu n is 0. Okay, so the point measured except from the measure 0, the function is the same. Then our claim is that g is a measurable. Our assumption is f is a measurable function, and this is same except from the measure 0, coincidence except from the measure 0. Then claim is that g is a measurable. Claim is clearly if we consider the collection of the x such that gx is greater than alpha, alpha is the arbitrary number, is element in the sigma algebra in x. Of course, xa, this R is the sigma algebra in x. In order to check this, we should see the almost everywhere. So define the set E collection of x is fx is not equal to the gx. However, this set this occurrence occurs in measure 0. So this means if we estimate its measure m star e is 0, and remember that when you consider general measure space, every outer measure 0 belongs to m star. This means all over the measure 0 is sigma algebra. In this case, is also applied into Lebesgue measure case. So we can check that E is the element in R. And if we express this set collection of the x greater than a alpha, you can separate this all when considering all of the case. If f is equal to g, in this case, this is the same. However, the problem takes place in the set E. However, we consider if the f in gx is the really considering point to the set E, even though this value is not equal, g is greater than alpha, or g is the smaller than alpha, including equation. So, and the set is the collection of the g x is greater than alpha. We can express this guy's element in E, gx is greater than alpha, but we exclude x in E such that gx is smaller than alpha. Okay, consider this. The parenthesis here. Then note that this guy is clearly measurable, because our assumption F is the measurable set, and this guys is subset of E. Okay, this guy is subset of E, this guy is subset of E. This means these two elements here and here is the measure zero because of this. And note that measure zero, all of the measure zero element in sigma algebra. So then we can express this set is again this is comes here, and by De Morgan's law can express this is okay. This is the complement. Okay. Then note that this is the measurable, this is the measurable, and the union of the measurable set is also measurable, and this guy is also measurable. Okay, measurable. So its complement is also the measurable sigma algebra, an element sigma algebra, and its these two elements intersection of these and these is also sigma algebra. So these guys contained in R. So Gx is also measurable